High Z redshift is a very large shift in an observed celestial object's emission or absorption lines towards the longer wavelength or red or lower energy side of the electromagnetic spectrum, parentheses Z greater than 1, close parentheses, compared to wavelengths measured in the laboratory, where Z is found from the relativistic Doppler effect for a flat geometry of space. Let's take a look at redshift in general. Redshift in general is a comparison of an observed spectrum compared to a laboratory spectrum. Now, the difference between just redshift and a high Z redshift is that the high Z redshift has a very large shift in the spectrum. So we have a large shift in the observed celestial object's spectrum. So here's the observed spectrum. This is an absorption spectrum. We see black lines on a colored background. The colored background is our continuous rainbow spectrum, from red on the right through orange, yellow, green, blue, indigo, violet on the left. We see this pattern of black lines, and we want to compare this pattern of black lines to that found in the laboratory. So we're looking at a hydrogen spectrum in the laboratory, along with some other lines, some other elements of the periodic table in the laboratory, and we're comparing that to the observed spectrum from a particular object. And that object is very far away, and we know that because we see a large shift in the lines. The lines all appear in the same pattern from left to right, but they're all shifted to the right side of the spectrum, which is the red side of the spectrum, or the lower energy side of the spectrum, or the longer wavelength side of the spectrum. It's the red side. Everything's shifted to the right compared to the one in the laboratory. So a high Z redshift is a very large amount of shift compared to a regular redshift. Now, the difference between a regular redshift and a large Z redshift is that a large Z redshift has this Z value greater than 1. So how do we determine this Z value? Well, Z is determined from the relativistic Doppler effect for a flat geometry of space. So here's the relativistic Doppler effect for a flat geometry of space. Flat geometry of space is like a sheet of paper. It's not curved, it's flat. And we want to find this redshift value Z. There's the Z value, or here's the Z value. So you have to decide, is this object, so let's say this is Earth, here's Earth, and you're pointing your telescope out into space and you're looking at some object. Is this object moving away from you? If it is, and you know its motion away from you, its radial motion, its velocity in the radial motion away from you, then you can use this equation here to solve for Z. If instead you only know the transverse motion or the perpendicular motion, so we'll call that velocity perpendicular. If you only know that value, well, then you would use this equation on the right to solve for Z. And if you find that Z is greater than 1 after you've calculated it out, you've got what's known as a high Z redshift. In other words, the object you're looking at is very far away from the point of the observation or your telescope.